So that's manual S. It's really about 4 metrics, and we've got a spreadsheet for you to help you do some interpolation. So things get really interesting when we go beyond manual S. And this is the part of our conversation where things start to get quite a bit more complicated, but I also think where things get really fun too. So manual S, like I said earlier, sets these guardrails, but it actually provides quite a bit of room for us to further dial in the design to deliver comfort and efficiency for homeowners. We're now going to get into some interesting trade-offs related to auxiliary heat, low load cycling, and overall kind of energy efficiency, and how some of those things impact comfort, upfront cost, operational costs.
2 quick announcements before we dive in. First, today's episode is all about Manual S, and we put together a free Manual S spreadsheet for cold climate heat pumps. You can download it on our website. The link is in the show notes. We'd love to hear what you think of it. Second, this one's a selfish one. Amply is hiring. We're looking for an iOS engineer to join our small but mighty team. Customer feedback on our software has been awesome, and we know exactly what we need to build next. But we need more hands to do it faster. If you or someone you know loves building great software and maybe has an oddly deep affection for HVAC and in particular heat pumps, check out the link in the show notes and please share it around. We'd love to hear from great people interested in the role. All right, on to the show. Hi, and welcome to the Heat Pump Podcast. I'm Ed Smith, co-founder of Amply Energy, and my guest today is my co-founder of Amply Energy, Eric Fitz. Hey, Eric.
Hey, Ed.
Thank you for joining me on our podcast.
You're welcome. I'm excited, man. This is going to be a good one.
I can't wait to make fun of you as we go through this. Eric has developed a training that he's delivered. He delivered at ACA National, BPA in New Orleans, BPCA New York event in Saratoga Springs, and it's gotten extremely good feedback. And it's incredibly pertinent to what this podcast is all about. It's about variable capacity heat pump selection, manual S, and beyond. So we figured we should do an episode on this. So Eric's going to run us through his presentation. This is our 3rd try at taping this. I think we're going to get it right this time. But we'll say it works well over audio. If you're listening on Apple or Spotify, I think it should be just fine. But if you can watch on YouTube, like Eric does have a bunch of slides, we're not going to try to explain those slides. That is extremely painful. But Eric's takeaways are quite clear from the audio. But if you want, might be a good thing to have up on YouTube to take an occasional glance at slides there. But with that preamble, Eric, I'm going to turn it over to you to share the insights that you have been sharing with others. And I'll just chime in with questions and comments as we go through.
Sounds good. So we'll cover a bunch of fun stuff here just to lay the groundwork before we get into manual S and things beyond manual S. We'll take a minute to talk about what are the heat pump characteristics, the ways that we measure their performance, both from a comfort and from a energy efficiency perspective. And once we're on the same page on that front, we can dive into manual S, and hopefully you will feel like after this conversation that actually manual S is pretty straightforward. And then we're going to get into some great real world examples and issues that are way beyond manual S that we think you should be aware of to help you do better designs. So things around low load cycling, auxiliary heat, and throughout we'll sprinkle in some best practices and some other great resources that are available. The impetus for this conversation was really around this feeling that heat pump design is complicated. And I also think it's really fun. And it's complicated because we're trying to balance a lot when we are designing a heat pump system, trying to deliver comfort and efficiency for our end customer, for the homeowner, with a big emphasis on comfort. But to do that, we got to be thinking about heating issues, whether or not we need auxiliary heat. What's going on with sensible cooling loads in the building and sensible cooling capacity of our equipment? What about latent issues? And all of these things lead into concerns around low load cycling. That all has an impact on operating costs for this homeowner that we're trying to design a system for. And then every one of these issues also has an impact on upfront cost of the system that you're trying to design, you're trying to sell. So it's a ton that we're trying to balance. The good news around all this stuff that we're trying to balance is that The Air Conditioning Contractors of America, ACA, has a whole design series that we can follow that's in a very logical sequence to help us do this work. We're mostly going to focus on two of them. Very briefly, we're going to talk about Manual J, and then really Manual S, obviously, is the focus for today. We need to touch on Manual J in particular because Manual J is the problem. This is what the home needs. And Manual S is a close companion to it because Manual J is an input into Manual S. And Manual S allows us to figure out what's the right solution for this problem. What is the right equipment that's going to work with this home and deliver comfort? And so the key takeaway here is that Manual S is worthless if you haven't first done accurate, thoughtful load calculations. This is the old garbage in, garbage out problem. So we'll take a moment to talk about Manual S, but I'll pause here for a sec, Ed.
Shout out to Alex Meany for the Manual J is the problem, Manual S is the solution. He goes on to say Manual D is the execution or distribution, obviously, but we're not going to focus on that today. Thought that was super clear. Thanks, Eric.
Nice. Awesome. All right. So just to touch on Manual J, remind folks that may not be familiar, Manual J, again, is what the home needs. It is a methodology for modeling the heat gains and heat losses in a home. And on the cooling side in particular, it allows us to calculate what's the sensible cooling load and the latent cooling load. And that's for conduction, convection, radiation that's happening in the home through the winter and summer seasons. And one shorthand that we often use to quickly understand the sensible and latent is the sensible heat ratio, or the SHR. This is a ratio of the sensible in the numerator divided by the total cooling loads, the sensible plus latent. And this will come up more later, but that's a common metric that we focus on, so the sensible heat ratio. And so the main point here is do a Manual J and be aggressive with your assumptions. We obviously plug to ourselves. We've got our own ACA certified Manual J product. There's a lot of other tools out there. Just do a Manual J. Be aggressive, meaning if you've got window treatments on your windows in the home that you're modeling, like blinds or shades, like assume that they're going to be used when it's design temperatures in the cooling season. And same thing on the heating side. So be aggressive, be thoughtful, verify those key inputs, and we'll have good outcomes.
We just taped a pod with Nate Adams on this topic. Since Manual J has some factors of safety in it, if then contractors are padding insulation and air leakage with more factors of safety, like they're being conservative, not aggressive, you end up with massively inflated loads. And then your Manual S is not going to be that helpful because your Manual J is totally off, like the two feed into each other. So that be aggressive is counterintuitive. At this point, we've onboarded, hundreds of users to Amply? And we see this over and over again. It's a real mindset shift. Don't pad your stats. Be aggressive, be lean, and you'll better number out to design a better system for the homeowner.
You nailed it. Let's dig into these performance characteristics of heat pumps. And we'll start with the thermal performance characteristics. I'm sure everyone's familiar. One of the unique aspects of heat pumps is that they're obviously providing heating output in addition to cooling. And the big challenge with heat pumps is that thermal capacity, the ability to transfer heat into or out of the building, varies with outdoor temperature. So for heat pumps, we have min and max heating capacities that vary with outdoor temperature. So meaning when the unit's running at a lower output, max when it's running at a higher output, but those values vary with outdoor temperature. And same thing on the cooling side. And we've got capacity characteristics both for sensible and latent. And there's a companion ratio that is helpful to pay attention to. Again, thinking about the cooling capacity for heat pumps, the sensible heat factor. And so this is the companion that goes along with the sensible heat ratio, which is from the home. Sensible heat factor is for the equipment, and it's just the sensible capacity of the equipment divided by the total cooling capacity of the equipment. And those are the core comfort metrics related to thermal performance. And this is what Manual S is all about. It's all about understanding the heating capacity, cooling capacity, and delivering comfort. On the flip side, we talk about energy performance. And the most common metric we think about first is the coefficient of performance, or COP. And then there's a couple other metrics that are derived from COP. You've got the SEER, the seasonal energy efficiency ratio, and then the HSPF, the heating seasonal performance factor. I'm not going to go into those a whole bunch of detail, but I'm sure you're familiar with them and have heard them over and over again. COP is the ratio of the thermal output of a unit divided by the electrical power input. And the amazing part about heat pumps is that, generally speaking, for every 3 to 4 units of thermal output that you get, you'll need to put 1 unit of electrical input. So this is the magic of heat pumps from an energy efficiency perspective. What's very interesting is that manual S is completely silent on these energy performance aspects. And this is part of the reason why we want to talk a bit more beyond manual S.
At the National Comfort Institute National Conference last September, David Richardson was given a great presentation. And he was talking about comfort, efficiency, a whole bunch of other stuff. And he said, in our industry, what do we typically sell on? And I think Tim DeStasio raised his hand and said efficiency and sometimes comfort. And he was not agreeing with that sentiment, but that's often what we do. And I think it's clearly what you're driving home on this slide. Like, comfort and efficiency both matter. Comfort first, comfort second, comfort third. That's what you're there to solve. And that's what ACCA's Manual S takes into account. But with heat pumps, like, efficiency is a question. And so it's an additional layer of complexity and analysis. And you're going to walk us through that. No mistake, even if we talk about that, it's comfort is the primary problem to solve for the homeowner.
Yeah, solve comfort, and generally efficiency will follow naturally. All right, so let's drill into some of these metrics in a little bit more detail. I'm going to use an example piece of equipment. I've got a bunch of data up from an engineering submittal around what its characteristics are at a bunch of different outdoor temperatures. So we've got cooling test points, or at least reported performance metrics. Some of these values are directly tested in the laboratory. Some of them are calculated. I won't get into all those details, but what are generally reported at a minimum are the 95 and 82 degree outdoor temperature performance characteristics for cooling, and then 3 heating data points, 47 degrees Fahrenheit, 17 and 5 degrees. There's an optional 4th data point. Is up to manufacturers what actual temperature they are reporting on or measuring. It could be -3 degrees, it could be -13, it could be -15. It's up to them if they want to include this as part of their performance metrics. So the cooling plus the 4 heating data points, that's across 6 different temperatures. And then because it's a heat pump, we've got min and max values associated with each one of them. And so if we use an example here, looking at heating data, so at 47 degrees Fahrenheit, this particular piece of equipment has just under 11,000 BTUs per hour of heating capacity, or rather minimum heating capacity. And we can do some math. Again, this test point may or may not have been directly measured in the laboratory, but we can do some calculation and say, okay, using the data that was pulled during laboratory testing, we've got a power input, and we can calculate what's the COP. So again, for this particular unit at 47 degrees Fahrenheit, we are seeing that it's got a COP of 3.23 at 47 degrees. And we can look at the same thing on the max side for this outdoor temperature of 47 degrees. So for this unit, we're at about 45,000 BTUs of heating capacity at its max output, and a COP, interestingly, that is even higher than the min, a COP of 3.64. So it's fairly straightforward, but it is a lot of data, both cooling and heating. So if you pull all the numbers, 4 different outdoor temperatures, min and max for each, we've got 8 different values just from the heating capacity, different values from an energy efficiency standpoint. The sensible capacity and COP data is pretty straightforward. The challenge comes in on the latent capacity side. Unfortunately, it varies quite a bit by manufacturer. If you are lucky, you'll get a table that looks something like this, where on the kind of vertical side of this table, it's varying based on the outdoor temperature. And then the horizontal axis of the table is we're varying the indoor entering air temperature across the coil in dry bulb or wet bulb temperature. And within the values in the table, we've got the total cooling capacity and then the sensible cooling capacity. Now we want latent, so the manufacturers are expecting us to do some math. So we just take the total cooling capacity from the table and subtract the sensible cooling, And that gives us the latent capacity. So a little bit of work, not terrible, but yeah, we just don't generally get latent values directly reported by manufacturers. We have to do a bit of math. However, sometimes they are directly reported. And for whatever reason, a lot of ductless manufacturers decided to report their latent capacity in terms of pints per hour. I don't know why this is. That's what you see often out there. Good news, again, we can do a little conversion. We know that there's roughly 1,000 BTUs of latent capacity per pint of water. So do a little math. And in this example where we're showing 3.8 pints per hour, that's equivalent to just roughly 4,000 BTUs per hour of latent capacity. And there can even be a third type of kind of format that you'll see the data where it'll look like the first table that I described, but instead of having the total cooling capacity and the sensible cooling, the manufacturer will report the total cooling capacity and the sensible heat factor. So you just pull those values from the table, and then again, you do some math, and you can calculate what the latent capacity is. So a bit more work, but it's doable.
Doable. I'll say, this being my third time, at least my third time through this, it's straightforward, but not necessarily simple. And certainly, it's more time-consuming than it feels like it should be.
Yeah.
But thank you for breaking it down. Like, I get it. And I imagine if you have your favorite equipment that you install over and over again, you start to know this stuff for that equipment pretty well. So it's tricky the first time you go through it. But I'd say it's a surprising amount of work for stuff that feels should be teed up more readily.
Yeah, that's a great point. Once you get to know your own equipment, you're going to see these tables over and over again, and yeah, be a lot more familiar and easy to work with. But yeah, it's definitely surprising the first time you come across this. All right, so now that we have an understanding of these different performance characteristics, we can start to think about, okay, how do we compare different pieces of equipment? It's very hard to look at dozens of different data points and be able to do that quick comparison for multiple pieces of equipment. So in order to make that comparison easy and intuitive, we often visualize the information. I'm going to do that right now. And typically we start with what's going on with the home. And so we can actually plot how the home loads using the manual J results are varying with outdoor temperature. So if we take, in this example, this is my house in the Portland, Maine area. I've got a 5-degree Fahrenheit outdoor design temperature. My design loads are 42,000 BTUs. I can just draw a point on a graph where I've got load on the y-axis and temperature on the x-axis. And I can draw another point down around 60 degrees Fahrenheit where I'm assuming that I won't need any more heating capacity in the home, or that the loads have dropped completely because the temperatures are so low, rather. And I can draw a line. And between those 2 points, between 60 degrees Fahrenheit and 5-degree design temperature, we can now visualize how the loads on the home are varying as the outdoor temperature changes. And we can do the exact same thing on the cooling side, draw a line between 70 degrees, where we'll roughly assume that cooling will be some kind of cooling loads in the home, all the way up to my design temperature of 83 degrees Fahrenheit. And I've got these two nice lines to understand how the home is varying. And then we can overlay those heat pump performance characteristics, those thermal capacity values, over the top of this same graph. And so I'm using the different outdoor temperature ratings, and allows us to draw a max heating capacity curve, a min capacity curve. And so it's very simple. So I just draw different points. So at 47 degrees, I have my min and max temperatures, 17 degrees at 5 degrees, and for this example, at minus 5 degrees. And so I can take all those max points and just connect them together with a line, and I've got a curve. And I can do the same thing on the minimum capacity. So it looks a little bit like an alligator with its mouth open for these two curves. And then we can do the same thing on the cooling side. We've got a max cooling capacity curve and a min cooling capacity curve.
Awesome. I'm keen to see what you do on the next one when you tie these together for what it means for the home and the equipment.
Sure. We're going to dig in a little bit further. And so we've got the capacity curves. We can also drop in the efficiency values, the COP values, which are varying with outdoor temperature and at these performance measurements or that were reported for the equipment. And this is a little bit harder to describe, but we can see that there's a bunch of different COP values. They're quite different depending on the outdoor temperature. And the question that we have as a designer is, what is the COP going to look like at different temperatures? And in order to figure that out, we have to look at where, in this example, let's say, what's the performance of the heat pump going to be at 17 degrees Fahrenheit? So I can draw a line between the min curve and the max curve for the equipment. And I can look at where that line intersects with the home load line. And that can help me figure out what's the actual expected performance for this specific home, for this specific piece of equipment. In this case, it's around a COP of 2.45 or 245% efficient. So that's a bunch of work. So some smart people came up with the HSPF and SEER metrics and doing some hand waving. It's a way of having a consistent process using a benchmark home to understand how those COPs are varying throughout the heating season, if it's HSPF, or how the COPs are varying for the cooling season with SEER. And so it's a way to, instead of having to look at all these different numbers, have one metric to represent that overall energy efficiency. Yeah, that's all the kind of foundation that we need to build on top of.
I'll say if folks are listening, this is a moment to look at YouTube because I think that graph is very helpful.
So let's get into Manual S. Manual S.
Let's do it.
It's all about this solution. We're trying to Goldilocks our system design. We don't want it to be too big. We don't want it to be too small. Really great thing about Manual S is that there's actually a brand new version that came out at the end of last year, and it is available for free for the first time just on ACCA's website. We'll drop a link to it in the show notes, but I strongly encourage everybody to check it out. Yeah, it just lays all this stuff out, and I think reading it just once, you'll glean a lot of useful information from it. But I'll give you the quick summary here. Manual S, its purpose is to provide what Manual S refers to as size limits to make sure that we're delivering comfort to homeowners. And so those sizing limits are around heating, sensible cooling, and latent capacity. And the other great part about this new version of Manual S, there's a bunch of other great stuff now that's there specifically for variable capacity heat pumps. There's some new sizing tolerances. There's a bunch of flexibility, both for dry climates as well as some scenarios when you're in a non-dry climate. And even if you've got a dedicated dehumidifier, you can actually size only using the heating characteristics, where in the past the guidance was to size based on cooling capacity, even for a heating-dominated climate. And so Manual S is a fairly lengthy document, goes into lots of details, but it's because it's designed for any kind of HVAC equipment. If we focus specifically on variable capacity heat pumps, things get simplified really quickly. So there's a whole complex decision diagram, and the most basic question is, are you sizing a heat pump? So the answer there is yes. If that's the case, you go to another diagram and decision tree, and it's pretty clear. Again, if you're focused on variable capacity heat pumps, the most basic question is, do you have dedicated dehumidification, or are you in a dry climate? And so we're going to drill into
that. Distillation is a heck of a lot simpler than those decision trees looked.
Totally. And the decision trees aren't that bad. Honestly, they look complicated because it's just a lot of things on the screen, but they are, again, I encourage you to check out Manual S, check out those diagrams. They're helpful, but it is nice to be able to jump to exactly what we want to focus on for the type of equipment we're talking about.
That is the good engineering student in you defending decision trees. I know why you're doing it, but you distill it nicely, like dedicated dehum, or are you in a dry climate? Like that is easy to remember.
Awesome. So if you are in a dry climate or you have dedicated dehumidification, that means you jump to this very specific advanced dry heat pump condition that is specifically section N2.3.4.3 of Manual S. We're going to skip going into that because we think most folks are in non-dry climates or they don't have dedicated dehumidification. And so in that case, we go to the new variable capacity advanced section of Manual S. And if you do that, all of it boils down to 4 heat pump size factors. And this is on page 24 of the new version of Manual S. Again, we'll drop that in the show notes. So these 4 factors, it's pretty straightforward. We've got 2 on the cooling side and 2 on the heating. And each one of these factors, all it does is take the ratio of some metric from the equipment and it divides it by a manual J output. So most of the time it's total load, either cooling or heating. And so the first metric is the min cooling sizing factor. And it's just looking at what is the minimum capacity of the equipment divided by the total cooling load of the home. And that just needs to be less than 0.8. So basically it's trying to make sure that this particular unit can turn down enough can ramp down enough for your application and not result in a bunch of low load cycling, like the most egregious type of low load cycling. And then similarly, we've got a min latent capacity metric, and we want to make sure that even at minimum operation of the equipment, we still are meeting 100% of the latent load in the home. Pause there. It's all making sense, Ed?
Yeah, it makes sense. I think your distillations were great. Does a turn down ratio turn down enough so you don't have a ton of low load cycling? And at its, can you handle at least 100% of the latent capacity with the minimum latent capacity of the unit? Makes sense.
So on the heating side, we've got a min capacity as well. It's just the perfect pair to the cooling side. Again, we're just making sure we can kind of ramp down enough to avoid egregious low load cycling. And then we've got a max heating. We want to make sure that we are at design heating loads. We've got 100% of the capacity needed to keep the home warm. So just 4 metrics, 4 simple ratios. I think it's pretty straightforward math. Now, there's one little catch here. All of these capacity values that we're talking about for the equipment, ManualS is very clear these are at operating conditions, which should not be confused with design conditions. So operating conditions of the equipment means you have looked at these expanded performance tables for the equipment at design day temperatures, and you've also made any corrections that are necessary for altitude, for line set lengths, whether you might have a multi-zone setup where you also have additional D rates. You need to take into account all of these different factors so that this particular piece of equipment operating in the environment that it's going to be in at design conditions, altitude, etc. Those are the capacity values you should be using to do this math.
This all makes sense. Also, you keep saying it's straightforward. The more straightforward steps you layer onto something, the more complex it gets. This is a decent number of steps, but like my takeaway here is for the operating conditions, are you picking equipment for heat pumps that are going to be able to serve both the needs of winter and summer? And as we know from previous episodes, like there's a direct trade-off there, right? Because if it's too big, just like our climate zones, right? I'm in Massachusetts, you're in Maine. If you oversize something for the winter, it's probably not going to ramp down low enough in the summer because the winter loads are so much higher, the heating loads are so much higher. And so you're going to have trouble removing that latent capacity. So just to your point a couple slides ago, this is driving home the math of Goldilocks sizing. You need a heat pump that is going to be able to serve both of these things. And so you can't just focus on heating or just focus on cooling. You need to think about it over the course of the whole year.
Yeah, I like to think of these ManualS size factors. These are just basic guardrails. And so we're just double checking that for a particular piece of equipment, are we within these guardrails that we're going to have a good outcome from a comfort perspective for the homeowner.
So and the point is, you want to ramp down below 80% and you want to cover at least 100%, depending on whether you're looking at minimum or latent or max.
Yep.
Cool.
All right. So really the challenge from my perspective comes down to not the math per se, but it's about how do you get your hands on accurate data for the equipment you're installing. Ideally, you should be able to find this from the manufacturer's extended performance tables that are within the design manuals or engineering submittals that are available directly from the manufacturer or maybe through your distributor. They can be pretty hard to track down in some cases. Often they're behind some kind of protected website, you need a password. Even if you have access, it can be hard to find the exact details for the specific equipment you're installing. However, it is the most granular and it is bound to hopefully will have latent capacity data. Unfortunately, there are cases where even the manufacturers in their engineering submittals are not reporting this fourth temperature for heating in particular. So for those folks doing cold climate heat pumps, it can be a challenge to find all those data points that you're looking for. There's a great additional resource from the Northeast Energy Efficiency Partnership, NEEP. They have the air source heat pump tool that allows you to easily search thousands of pieces of equipment to get the min and max capacities at the kind of the biggest range of outdoor temperatures, particularly for those heating temperatures. The big gap on NEEP's database is that as of today, it doesn't have any latent capacity data. Although There are rumors that they are working on that. So just a shout out to Neep. They're aware of this and they are trying to figure out how we can get some more latent data into their platform. So between these two sources, you should be able to track down most of what you're looking for, but often you're really going to have to go to those manufacturers' tables to get that latent capacity information.
It's amazing to me this isn't more readily available, but I know that's like a whole topic for another day.
It's a big challenge. So next time you're talking to your brand manufacturer rep, you're talking to one of the big brands directly, remind them that it's hard to do your job if you don't have the right data to make decisions. So let's get these manufacturers to report latent data in particular. All right. And then the next challenge is, okay, so at the beginning, we talked through a bunch of these heating thermal performance metrics at different temperatures. And if you remember, they're typically at 47 degrees Fahrenheit, 17 and 5. So what happens if your local design temperature for the project you're working on is, let's say, 9 degrees Fahrenheit, right? So you're like vaguely halfway between ish 17 and 5 degrees Fahrenheit, but not exactly halfway. And so you've got to do some kind of math to figure out, okay, given that the different heating capacity values, both minimum and maximum, are reported in this particular table, and I'm at somewhere between, I need to do some kind of linear regression or interpolation, which gets to be a real pain in the ass if you're doing it for a bunch of different data points. You've also got to do this for cooling, sensible, latent. It's a bunch of work. And so that's where most people start pulling their hair out. And good news here is that we've actually felt we could help out. So we've got a free spreadsheet tool that does that interpolation for you. We'll drop it into the show notes. It's designed specifically for variable capacity heat pumps and will help you figure out whether you're manual S compliant or not. So you can just take the equipment you typically install, grab the data and save it in the spreadsheet, and you can just use it over and over again for your various projects, and makes it real simple.
There's a lot of drum roll of all the ways this is layers of complexity to say, hey, we've done it, made it super easy for you. But this is great. We've gotten great feedback on it.
Yeah. All right. So that's manual S. It's really about 4 metrics, and we've got a spreadsheet for you to help you do some interpolation. So things get really interesting when we go beyond manual S. And so this is the part of our conversation where things start to get quite a bit more complicated, but I also think where things get really fun too. So manual S, like I said earlier, sets these guardrails, but it actually provides quite a bit of room for us to further dial in the design to deliver comfort and efficiency for homeowners. We're now going to get into some interesting trade-offs related to auxiliary heat, low load cycling, and overall kind of energy efficiency, and how some of those things impact comfort, upfront cost, operational costs. We're not going to get into a bunch of details around airflow and duct capacity, which are super important, or things like system layout or commissioning. That's for a whole other conversation. So we'll come back to the graph that we were looking at the beginning, where we've got the home loads, both the heating and cooling, and then the capacity of the equipment, the max curve and the min curve for heating, and the max and min curves cooling. And we can start to look at different parts of this graph to talk about what's going on. So in this middle zone, what I have highlighted green on this slide, this is the area where the outdoor temperature is such that the loads on the home are in between that max heating curve and that min heating curve, or the max cooling curve or the min cooling curve. This is the happy place for the heat pump. This is where the heat pump's modulating and can exactly match those loads of the home and get those maximum run times. It's just cranking away. Things are good.
If you bring that one back, Eric, like this is where people are always saying that with a variable speed heat pump, it ramps down, and so it can cover you much better, and so you're happier for much more of the year, and that's demonstrating this. But if you have a system that's oversized, you're basically moving the jaws of that alligator up, and so the amount of time the home is not in that happy zone is increasing, because no piece of equipment goes all the way down. They all have a bound within which they work, and so you want to make sure that home is in that happy band of max and min performance for as much of the year as possible.
Totally. That's where you get great energy efficiency. More importantly, that's where you get maximum comfort. You've got the equipment's continuously running, so you've got great air filtration, which is really important for indoor air quality. You also ensure that you're really bathing all of your surfaces in the home with heating or cooling, which results in you get your mean radiant temperatures are where they should be to maximize comfort for the occupants. So you started to allude to this, another kind of region of the curve, which is what happens when the home loads are higher than what the heat pump can actually output. I've drawn this in as this little red triangle in the upper left. So we're, for this particular piece of equipment, around 10 degrees Fahrenheit, the home loads start to go above that maximum heating capacity line. And this is where we need some auxiliary heat. And so Manual S says we only, for variable capacity heat pumps specifically, we only need auxiliary heat to cover up to the design temperatures for the project. But there's a whole other region going even colder than design temperatures where it's technically optional, but recommended to have some additional heat strips or furnace if you're doing a hybrid system for those few times of a year where you're going to have colder temperatures. It's not required for variable capacity because, as the curve is showing on this particular chart, the heat pump's still operating way beyond -5 degrees Fahrenheit. It can output something, so pipes are not going to freeze. The thermostat might drop a bit if you didn't have any auxiliary heat beyond that temperature. But again, for home comfort and also just peace of mind, if you had some kind of emergency where the compressor died in the middle of the winter, at least you know the homeowner is going to have some extra capacity available as backup, so it's not a crisis to get out there and fix the equipment.
This is the Ed Janowak. If you spend too much of your time focusing on the 1% of the year, that's in red right here, then the homeowner will be less happy for the other 99%. And so it's important to focus on bulk of it. I know you're going to get into amount of hours spent into these, but it's beautifully shown on this slide that that red is scary, and most people focus on that a bit more than you need to based on the number of hours you spend there.
Great point. All right, so then we can look at the flip side. What happens when the home loads are lower than the heat pump's minimum capacity, both heating and cooling. And this is where we run into low load cycling. The unit is satisfying the thermostat and it's shutting off because the loads in the home are so low. And this leads to all kinds of bad stuff. And so we now have this graph where we've got these different kind of colored triangles that give us a kind of a visual sense of how bigger the filled in triangle, the more auxiliary heat or the more low load cycling is happening. And that's useful for a quick visual. But what's interesting, we can actually quantify exactly how many hours a year we're in these low load cycling or auxiliary heat regions if we overlay in some additional data. So I'm showing a temperature bin graph overlaid on top of this chart we've been looking at for the Portland, Maine. And what's fascinating is that you can see, if we look at the auxiliary heat side of the chart, there's like dozens of hours of the year where we're colder than 0 or -5. As we get up closer to 10 degrees, which is where the auxiliary heat started to be needed, it bumps up a little bit, but it's relatively few hours. And if we do the math for this particular example, it's about 200 hours total for the entire heating season that we might need some auxiliary heat. And we can do the same math on the low load cycling region, which looks to be more problematic. So roughly 14% or almost 1,000 hours of the heating season, we're going to be low load cycling. And the cooling is even worse for this piece of equipment. We've got 37% of the cooling season, or 700 hours, we're going to be low load cycling. All right. So that was it.
I love this chart.
Quick look at, sorry, go ahead.
I love that chart. For anyone listening right now, would be a great time to check out the YouTube, because this chart is extremely compelling and ties it all together, everything Eric's been leading up to.
All right, so now we're going to look at a bunch of different pieces of equipment, specifically 3. And so the example we've been using so far is for a 4-ton piece of equipment. That's the label, the marketing label that's on this piece of equipment. And we're going to overlay a 3.5-ton unit on the same chart. And it looks totally different. And counterintuitively, this 3.5-ton piece of equipment, so it's from its kind of generic label, it's a quote unquote smaller piece of equipment. But for those of you that don't have access to YouTube right now, the max capacity curve is way higher. it actually has way more heating capability than the 4-ton unit that we were previously showing. And the max cooling and the cooling curves are also very different, the max cooling and the min cooling. And I'll throw on a third piece of equipment. This is a 3-ton unit. It, again, has a very different set of curves, both on the heating side and the cooling side, but in different ways. So like this 3-ton unit, confusingly, actually has more heating capacity at 5 degrees Fahrenheit at design temperature than my 4-ton unit. But the 4-ton unit at 17 degrees has more capacity than the 3-ton unit. So it can be very counterintuitive. And honestly, one of the main things I want to emphasize for folks, particularly in colder climates, when you're throwing around pieces of equipment and their labels are 4-ton, 3.5-ton, 3-ton, that means essentially nothing in terms of heating capacity. That labeling system comes from the pure AC days and is really talking about the cooling capacity. And so particularly for the modern cold climate heat pumps that are out there, variable capacity units, like you really got to be looking at the performance data to understand heating capacity. You can't just reference the kind of marketing 4-ton, 3-ton labels.
That's wild, actually. Just hearing how people talk about these things in the field, like to see this laid out this way and the dramatic differences in capabilities is pretty amazing.
Yeah. And it's fascinating, like these pieces of equipment, these examples, this is real equipment. It's some of the best brands that are out there, highest performing pieces of equipment, but just very different characteristics, very different looking curves. All right. So if we take this 4-ton, the 3.5-ton, and the 3-ton unit that we were just talking about, we can do the same thing to make these little triangles to figure out how much auxiliary heat or how much low load cycling is happening. And we can also take a look at manual S. And what's fascinating, again, for this example, which is my house in Portland, Maine, all three of these pieces of equipment, a 4-ton, a 3.5-ton, and a 3-ton, they all meet manual S requirements, which is also wild. This gives you a sense of how relatively wide these guardrails are, and also just how important it is to really look at the data as opposed to just rely on the labels for equipment. But what is quite different across these 4 different units are these other factors we've been talking about. So how much auxiliary heat you need, so like how many hours a year, and how much of the year will you be spending doing low load cycling, both heating and cooling. So the 4-ton unit, turns out it actually needs the most auxiliary heat, the most number of hours with heat strips running relative to the other equipment, but it actually has the least amount of low load cycling. The 3.5-ton unit, it has the worst. So it's the highest amount of low load cycling. On the cooling side, it's going to be cycling almost 60% of the cooling season. But the big difference is that it doesn't require any auxiliary heat because it has so much more heating capacity. And the designers of this piece of equipment, they were making a trade-off. They wanted this unit to have more heating capacity, and nothing's for free, so there was some impact on the cooling side.
These are all ducted equipment.
Correct. Yep.
Okay.
Yeah, and then the 3-ton unit is somewhere in between. It needs a little bit of auxiliary heat, so about 1% of the heating season, those heat strips will be coming on. And it's 20% of the heating season will be low load cycling, and 50% on the cooling side. Interesting trade-offs between these different pieces of equipment. They also all have different HSPF and SEER ratings, so different energy efficiency ratings. We can now look at that as well as another trade-off. So between the 4-ton, 3.5-ton, and the 3-ton, the 4-ton has the HSPF of 9.5, and the 3-ton has an HSPF of 10. So in theory, the 3-ton is more efficient in the heating season relative to the 4-ton. But the 4-ton has a 22 SEER, and a 3-ton only has an 18 SEER. So before I reveal again for you, Ed, which one of these do you think is going to use the least amount of energy?
I think the 4-ton is going to use the least amount of energy.
Okay. Interesting guess.
You guys can tell if this is our third, if this is our third attempt at this, we never made it to this slide before. I'm wrong.
So the 3-ton, at least according to the modeling, will use about 10% less kilowatt hours per year than the 4-ton.
I was way wrong.
And this is really driven by, in this particular example, in this particular location, it came out this way because in Portland, Maine, we got a massively dominated heating season relative to cooling. So the SEER rating on this 4-ton unit, that would have you would end up with likely being the most efficient unit if you were in a mixed climate where you have a bigger balance between cooling and heating season, or definitely a cooling dominated climate. So I just wanted to point out for this example, it looks like the 3-ton uses the least amount of energy, but it depends. It depends on where you're located for a given piece of equipment of how this is going to play out. The last nuance here is that ultimately, so energy efficiency for the sake of energy efficiency, love it. It's great. Let's reduce our energy consumption. That's a good thing to focus on. But what homeowners really care about is actually operational cost. And that is a combination of how much electricity you're using and what your utility rates actually are. And this landscape is really changing quite quickly. So here in the state of Maine and a number of other states across the country are starting to offer specialized rates specifically for heat pumps. So where I live, we've got a standard electricity rate that's around 23 cents a kilowatt hour, but there's a heat pump rate that in the heating season, so October through May, it drops in half. It's around 11 cents. But in the summertime, it jumps up to about 35 cents a kilowatt hour. But because I'm in a heating dominated climate, that actually works out great from an operational cost perspective. If we pretend we are at this heat pump rate and we compare the 4-ton to the 3-ton. So the 4-ton was the least energy efficient. It used the most amount of electricity. The 3-ton used the least amount of electricity. And we're assuming both of these pieces of equipment are on the heat pump utility rate. We only end up with $70 difference for the entire year. And this is both for across heating and cooling seasons, only a $70 difference in impact for the homeowner. And so at that level, I might not really focus a whole lot on the energy efficiency. I would start to drill into other things that I can do to really dial in the design or equipment selection for this project to really help out on the comfort side. Because energy efficiency, again, for this example, with these utility rates, it just doesn't matter a whole lot.
I love it. It's, again, each piece you've had here is straightforward unto itself. And as I look at this, it's awesome to see. It's a tremendous amount of work to deliver these sorts, if you actually want to deliver these sorts of answers to a homeowner.
Yeah, totally. We'll talk about that more in a few minutes, but yeah, it's a lot. All right, so let's summarize everything that we've gone through. We've looked at these 3 different pieces of equipment, a 4-ton, a 3.5-ton, and a 3-ton. And we've got a bunch of comfort characteristics. This we're going beyond manual S. All of these pieces of equipment, we've already checked. They are manual S compliant. We're good to go there. But now we're looking at how many hours a year, what percent of the heating season are we going to need auxiliary heat? How much time are we spend low load cycling? And then we also have these energy efficiency numbers. So we've calculated the kilowatt hours and the total operating expenses for the homeowner for the year. And I'm not going to go through all what we're showing on the screen right now, but it's a nice little table, which is just showing the comparison across all these different trade-offs. And so ultimately the question is, in this example, which one of these systems, the 4-ton, 3.5-ton, or 3-ton, is the quote-unquote best for this house? What do you think?
I'm going to go for the 4-ton again. It's the minimum low load cycling. And so I think that's going to maximize comfort. And given it's a $70 cost difference in terms of your electricity bill between that and the 3-ton, which is the next best for low load cycling, I would go with the 4-ton.
Love that. All right. So the thing I love about this is that it's a trick question, is that may be the quote unquote best solution for this house, but it really depends on very specific trade-offs you need to be thinking about. So comfort and energy efficiency is one of them, but that 4-ton unit, we're saying we've got to have heat strips and it's a decent amount, but maybe this home only has a 100 amp panel. The local utility, it's going to take 6 months for them to do a service upgrade to get them to 200 amps. Or homeowner just doesn't have budget for that extra several $1,000s to put in the heat kit. And so if that's a constraint you're up against, maybe that 3.5-ton unit is actually the quote unquote best system for this house because it doesn't require any auxiliary heat. Or maybe there is budget to do auxiliary heat, but instead of spending it on heat strips, you could just put a little bit more insulation on the duct system. The ducts are up in the attic. It's an old ductwork. It's put in 60s. And if you could just bump it up to R8 or even R6, all of a sudden your loads drop. And then actually you don't need any auxiliary heat still with that 4-ton heat pump. So there's a bunch of different things you got to think about. And the point here is that you can't just cookie cutter this stuff. If you really want to dial it in, you can use a good guide like Manual S, but you need to be thinking about the needs and the situation of your particular project. What are the goals of the homeowner? What are the constraints of the house? And how do you dial in your design to navigate those challenges?
And Eric, I should know this answer, but I'm staring at it right now. The kilowatt hours are less for the 3.5 ton, but the expense is more. And that's because a lot of those kilowatt hours are used during the cooling season when there is no heat pump rate.
That's right. Yeah. If you remember, that 3.5 ton unit had terrible cooling performance, both lots of low load cycling and pretty poor SEER rating. And so, yeah, that's bumps up quite a bit in that cooling season because of that.
It drives home for me the amount of local expertise, know your equipment, like sticking to a brand and having a bunch of units that you know really is super powerful. But this heat pump rate, knowing the electrical rates in various towns, and in Massachusetts, it varies town to town. Man, the amount of local expertise, and I think that's extremely powerful, actually, for HVAC installers who are focused on a geographic area to be trained up and know this sort of stuff because they're serving the same towns over and over again.
All right. So at this point, if you haven't already been thinking it, or as you've been listening or watching, you're probably thinking, you're out of your mind. This is not really possible to do. This is crazy. You're right. I think it's insane. I don't expect anybody to be generating all these different curves and looking at all this data at the level of detail we just have talked through. And that's because there's great tools out there that help you with it. So this is another plug for the Neep tool that I mentioned earlier, where you can pull up some data. They have what they call a system sizing tool. This is really intended to help with these issues that are beyond Manual S. It is not a Manual S replacement, to be super clear. It's really around these other issues we've been talking about. So you can put in your Manual J loads, and then it'll generate these cool little curves for you so you can visualize how much auxiliary heat you might need or how much the time you're going to be spending in low load cycling, both for the heating season and the cooling season. And they will calculate using these temperature bin data sets how many actual hours you're going to need supplemental heat or what percent of the year you're going to be low load cycling for cooling. It's a great tool. Check it out. That makes all this stuff totally accessible. All right, so Ed, let's wrap things up. So our takeaways and next steps, again, from saying what we said at the very beginning, prioritize comfort, focus on comfort, and then consider efficiency. Generally, if you focus on comfort first, efficiency will follow. Absolutely do load calculations. You use Manual J certified software. Be aggressive and be thoughtful. Verify those key inputs so you get a good Manual J so that you can then do an accurate Manual S. And this stuff feels a bit overwhelming if you've never done it before. Most installers, most contractors, you're probably putting in maybe 10 different pieces of equipment, like 99% of the time. It's even smaller number if you're mostly doing ductless. So just pull the data for the 10 or so pieces of equipment and save it in our little spreadsheet. So you just always have it handy. You don't have to keep going back to and looking at these super complicated engineering manuals. You just have the data at your fingertips. That's what matters. So just grab that data, and then you can use our free little Manual S spreadsheet tool to do some quick checks on projects. And so it's relatively few numbers, and you just swap in and out to make sure that you're within those guardrails of Manual S. You certainly, if you're ambitious, you can go to Neep's website and check out their air source heat pump tool so you can get into these additional trade-offs. Again, I recommend doing it for your most common equipment in a few kind of example homes so you can see if there are big trade-offs between the equipment you typically install, or if you see that there aren't big ranges, that you don't have to do it every time, right? You can just use it as a guiding principle for your most common projects. And if you are in a home that's really wacky, maybe you'll spend the extra time to double check that in the Neep tool. Little plug for us, little shameless plug. We are working on making this stuff way more accessible. We think it's crazy that we our folks are expected to do a lot of this stuff on their own. We want to make this totally accessible so that you've got manual S immediately done as soon as you've finished your manual J, and have these things like energy forecasts and electricity bill forecasts. So we're working on that here at Amply. More on that soon. That's it, Ed. Anything else you want to add?
Thanks for doing that. It was awesome.
It was fun.
And I'm delighted. Third time's the charm. We made it all the way through. Eric Fitz, thank you for joining me on our podcast, the Heat Pump Podcast.
You're welcome, Ed. It was super fun, and I'm looking forward to flipping things around and have you lead one of these sometime soon here. This was great.
All right. Thanks, man.
Thanks for listening to the Heat Pump Podcast. It is a production of Amply Energy. And just a reminder that the opinions voiced were those of our guests or us, depending on who was talking. If you like what you've heard and haven't subscribed, please subscribe in your favorite podcast platform. We'd love to hear from you, so feel free to reach out. You can reach us once again at hello@amply.energy, no.com, just .energy. Thanks a lot.